Imagine you have a big data set with loads of features and you want to build a predictive model. What could go wrong? Well, those models turn out to be too expensive in terms of computational resources or in terms of data collection. They often suffer from the curse of dimensionality, which means they often learn from irrelevant or noisy features, and the lack of interpretability. For this reason, we often apply a pre-processing step, which is feature selection. So we have our big data, we apply feature selection, get a smaller set of features, and then apply learning algorithm and get our model. What if we apply small perturbations in our original training set? Well, we're going to observe some variability in our predictive model, and this is what we refer to as the variance, and with the well-known bias variance decomposition. And this depends on the whole pipeline. So what if we looked a little bit earlier? What happens there? This is what we call stability. So stability is an analogous concept to the variance of a predictive model, and is defined as the sensitivity of the feature selection output to small perturbations in the data. So this has become growing area of research for many reasons. In some words, it is said to be an indicator of the reproducibility of the feature selection procedure. In biomarker identification, the stability is often said to be as important as the predictive power of the model. Also, for instance, in early cancer detection, the instability of the feature selection procedure has been a major obstacle to clinical applications. So, how do we measure stability? Well, there's been plenty of proposals in the literature. From 2002 to 2013, many papers propose a measure, and some other papers pick up one of these measures. So there's many differences in the chosen measure. So how do those roughly work? So the main structure is that, so we have the original data set, you take M samples of these data sets, you apply feature selection, which gives you M feature sets, and then you need a stability measure phi that will take as an input those M feature sets and return a stability value. So in most cases, what happens is that people pick up a similarity measure that will measure the similarity between two feature sets and then take the average pairwise similarities as a stability value. So, we can wonder, what are the properties we need, the required properties, so that the stability measure values are interpretable and comparable in different settings? So first of all, I'm going to introduce a little bit of formalism. So we can model a feature set of length d by a binary vector of length d, where 1 means the feature has been selected, a 0 means the feature has not been selected. For instance, here, features 1, 2, 3 have been selected, and here, features 3 and 5 have been selected. Okay, so if we repeat this procedure m times, we get a matrix with m rows for each feature set and d columns for each feature. So this will be the input of our stability measure. So now we're going to go through a set of required properties. First of all, some feature selection algorithms don't guarantee to return a constant amount of features. For instance, if we look at this matrix, sometimes 3 features are selected, sometimes 2 features are selected. So we would want a stability measure to be applicable in this scenario. Well, surprisingly, some of the measures are not defined, which is why this is our first property, to be fully defined. So which means defined for every possible set of features. So, the second property is that we would like a feature stability measure to be bounded. So if you look here on the left, this matrix, the two first features are selected every time, which means this is a fully stable case where there's no variation in the selection. So we would like a value to correspond to that, a maximum value. Conversely, we can look at this situation where the features are selected randomly, and this corresponds to fully unstable case. So we would like as well to have a value corresponding to that, which is why we would like phi to be bounded by constants. So, a third property, again let's look at these two scenarios. So here we have three features on this matrix. The first three features are selected every time, which means it's a fully stable scenario. Same for B, except that 4 features are selected. Well, these are two scenarios that are fully stable, so we would like, as well, our stability measure to have the same value. Well, in some cases, it might be the case that using, for instance, if we use less Garda measure, this will give a value of 0.6, and this will give a value of 0.8, which means we would say this one corresponds to a more stable case than this one. So we get the property that if all feature sets are identical, then phi should reach this maximum. Let's look now at this scenario where half of the time our feature selection procedure selects the first 3 features, and half of the time 2 of them. Well, here clearly there's some variation in the selection of the features, and some measures might return the maximal value. For instance, WALD and CWRL reach the maximum value of 1. So I've now the bi-implication, that is, phi should reach its maximum if and only if all feature sets are identical. Okay. Last property. Imagine now you have plenty of features to choose from, and you have a random selection of 2 features. If you repeat this many times, it is very unlikely that you will pick up the same 2 features because it's a random selection. But what if you're given a smaller choice of features? Then if you pick up randomly 2 features, a lot of feature sets will have selected the 2 first features because it's given less choice in the features. So we formalize this property as we would like on average phi to have a value of 0 when the selection is random. And this is called the property of correction for chance. All right. So now what about all these proposals we've seen? So we studied all these measures, and in this table we looked at which measures had which properties. And so it turns out none of the measures have all the properties. But we can look at this one, Riva 2007, that is the most widely used in the literature because it has all properties, except it's not fully defined. But when it is defined, this is the favorite choice in general. So several extensions have been proposed, but somehow they lost some of the properties. So we found out that if you used, so we explored the similarity measures, and it turns out if you use the sample Pearson's correlation as a similarity measure, then the resulting stability measure will have all the properties. More interestingly, when the feature set size is fixed, these 2 measures, Riva and Pearson, are equal, which means Pearson's is actually a generalization of that measure. So now these are 3 scenarios to understand how this stability measure works, so using Pearson. So here on those graphs on the x-axis, we have the feature index, so feature 1, 2, 3, and so on. And on the y-axis, we have the observed frequency of selection of the features over the M repeats. So in this scenario, this corresponds to a fully stable scenario, where the frequencies, the observed frequencies are either 1 or 0, which means the features are either selected on every set, other than never selected. And here we get a value of 1. Another scenario is when we have frequencies close to 1, some close to 0, so we lose in stability. And here is a random selection case where all the observed frequencies are equal, and in this case, we get a value of 0 as we expect. So we ran some experiments, and so we used L1 regularized logistic regression with regularizing parameter lambda. And so this is a model that implicitly performs feature selection, as the weights that will have a value of 0 can be considered as not selected. And so generally what we do in this scenario is that, we try several values of lambda, and then we look at the one that maximizes the accuracy, and we select a lambda. So can we increase stability without any loss of accuracy? So here we have a graph. On the x-axis, we have the error. And on the y-axis, we have the stability using Pearson's correlation coefficients. And each of the points here corresponds to a value of lambda that is a best trade-off between stability and error. So each one of these points is optimal in the way that they either minimize the error and maximize the stability. All right. So if we look at this value, this would have been the value of lambda we would have picked if we were basing our observation only on the error, because this is the smallest error. But, and in this point, this is the point we would have picked if we looked at stability only. But there is a trade-off in the middle. We can select this value of lambda that does not increase the error a lot and improves the stability. So we found an optimal Pareto trade-off, minimal error and maximal stability. So interestingly, in our experiments, by doing this, not only the error was not increased, but as well, only relevant features were selected in our model. So increasing stability brings more confidence in the features selected. And we advise to use Pearson's correlation because it has known properties. So there's more details about the experiments. There's more experiments in the paper. You can come talk to me in the poster session. And the code is available online as well in MATLAB, if you want to. Thanks a lot.
Thank you. Time for questions. You was first.
Hey Sarah, nice presentation. Teaser question. Have you thought about extending this to groups parsing? Do you think it would be easy or not?
No, I haven't looked at that. What I've been looking at so far is I've been looking at stability when they return rankings or when the feature selection returns a ranking or a weight on the features. But this is so far what I've been looking at. There's also stability theory in other fields or in, for instance, in PCA or these things, but this is out of the scope of what I've been doing so far. Yes?
Please.
We have been using stability as a concept important in bioinformatics, especially in very diverse
results from different algorithms in the same data set, in which there's a lot of correlation between variables. So it's easy to have strong changes in the list. Did you try working on this kind of situation in which you're expecting very strong correlation between blocks of variables, and then cannot be really sure that you want to get rid of the hypothesis?
So yes, this is something that is usually observed that when the features are highly correlated, yes, it turns out to be less stable. So in the paper, we used an artificial data set, and we generated several data sets with different levels of correlation between the features. And we observed that it tended to be less stable when there was higher correlation. So in the example here, this was correlated features, because when the features are uncorrelated, we can reach maximal stability and minimal error at the same time. So far, this is what we have been doing, but this is very interesting to study the impact of the correlation between the features on the stability. Yeah, so we observed that behavior. Yes?
What is the sensitivity of your proposed method with respect to the dimensionality of the original feature set?
So the whole thing, the whole point of these required properties is that it's not sensitive. It doesn't, so our stability value won't depend on the total number of features or on the number of features selected, which was one of the flaws that the other measures had. So by enforcing correction by chance, and that the values are bounded and so on, we make sure that all stability values are comparable in different settings. So there's no sensitivity to the dimensionality of the original